video up here for my online class. So I'll turn it over.
All right, awesome. Well, guys, I know most of you. I've had you probably in one of these courses before. Hello, everybody online. I've probably had you somewhere before. So the purpose today is a little bit different than my normal classes. So if you had me in class before, those are a lot more informal, and to some extent this will be pretty informal as well. But this is a lot more like a conference presentation than it's going to be an actual class. So I'm going to show you lots and lots of stuff, and then I'm rarely going to stop and say, hey, let's work some examples of these things. I mean, we're just going to go through and remind you, for the most part, about the stuff you've already had. So by virtue of you being in Capstone, you've probably gotten through, or at least more than halfway through, your statistics and methodology sequence, Psych 3330 and Psych 3435. This is, to every extent possible, a 1-hour summary of a year-long course sequence. So as you can probably guess, there's going to be a lot of stuff missing from my presentation today. There's just no way to cover it all. What this was, basically the way I constructed this yesterday was to go and actually, we looked at some preview versions of this major field achievement test and just looked at the kinds of questions that you guys are being asked. And for me specifically, I looked for questions that you should be able to answer based on your experience in your statistics and methodology sequence. And I know many of you are probably thinking, I don't remember how to compute t-test, or I don't remember exactly how to compute the F statistic for an ANOVA. That's okay. The fact is, the major field achievement test is not going to ask you to do that. It's going to ask you to know conceptually when would you use an ANOVA versus when you would use a t-test. But it's never going to ask you to compute something. Most of the time, we assume once you get through the undergraduate curriculum in psychology that you know what it is you're dealing with, and you probably have some experience using some computer software, if not the hand computation. So again, the big focus for us is what and why, not necessarily how. Okay, so if you don't remember specifics, that's okay. The purpose of today is to jog your memory with respect to a lot of these things. Okay? Are there any questions just about that before we go on? I'm going to go ahead and just kind of give you a quick overview of what it is that we're going to be covering today. So while this is up here, now's the time for questions. And guys, feel free to ask questions during the middle of the talk. I can't just sit and talk to you for an hour. I like to talk with you. Okay? I have to stop for questions, otherwise, how would I drink my coffee? Okay. So what we're going to do, again, this is a sample. It's not a random sample, no pun intended for this class right now. It's a sample of the topics in our statistics and methodology sequence, and these are some of the important ones. We're going to talk about describing data, okay, otherwise known as descriptive statistics. In the way I teach statistics, this is about the first 3 or 4 weeks of the course. We're going to talk about z-scores and then their natural lead into one of the most important distributions for this major, that being the normal distribution. And we'll talk about normal distributions in relation to z-scores. And then we're going to move for the last half of the lecture on the inferential side. We make the transition from describing data to now using data to infer things about people we can't see and about populations that we can't possibly test. So the inferential statistics will review what hypothesis testing is. We'll review the statistical tests and the common experimental designs that we talk about not only in statistics but also in our research course. And then finally, I want to give a review of some non-experimental designs, which surprisingly, I guess for me, because I'm an experimental psychologist, there were a lot of questions on the major field test that I saw reviewing non-experimental stuff. So we need to make sure and cover that. If for no other reason than I don't typically cover it enough when I teach research. So there you are. So let's go and let's jump right into it. Let's talk about statistics and why we use them. Okay, I know it's a strange way to characterize statistics as a plural, but it literally is. There are a lot of statistics. That's hard to say. Statistic is a single measure of a set of data, right? There's a statistic that measures the center of data. There's a statistic that measures the spread of data. So when we talk about statistics, we're literally talking about a plural thing, a bunch of descriptors of data. There are statistics that tell us about the relationship between a sample and a population. Those are so-called inferential statistics. So what are these things and why do we use them? Well, once again, most of our statistics course is broken into two halves. You've got the descriptive part, where we learn how to describe data, and things that we do typically are we describe our data in this sort of context as distributions of scores. And you're always talking about the normal distribution or a sampling distribution or all these things that you talked about at some point. So we use statistics to describe, but we also use statistics to infer. Again, the last half of your statistics course, actually more than probably about 2/3, is we talk about how do you take small samples and then infer to a much larger population based on that very limited subset of things that you've got. For example, when I do research, I might have a research question and I get 30 or 40 of you guys in the lab and I measure you somehow, and then I'm supposed to be making an inference to basically all normal adults from there. Okay, how do I do that? There's a lot of people that are missing from that sample. Well, again, the idea, the game here, so to speak, is we take that sample and then we compute something that lets us infer up to that population. So hence the difference between descriptive and inferential statistics. One of the key questions that we always ask with inferential statistics, whenever you do a statistical test, whenever you're doing this hypothesis testing thing that we'll talk about in just a little while, you're always asking yourself, are the results that I'm seeing above and beyond what I would expect from chance alone? The idea is that anytime you bring a set of humans into a collection, either giving them a survey or some behavioral experiment on a computer or hooking them up to an EEG or whatever it is that you're doing, whatever it is that you're measuring those humans with, there's always error involved. There's always the notion of random chance involved. And we want to know if we're seeing differences between males and females or between this condition and this condition, is that just those measurement differences? Or is it really something about the difference between those two populations that's causing this difference? So that's kind of the big question and the reason we do what we do in statistics and the reason we design good experiments in our research methodology. So let's talk about distributions real quick. There are many important distributions of data that we deal with in a statistics course. There's the population. Remember that the population is a set of all scores that we're interested in. So your population will differ as a function of what you study. If you are a developmental psychologist, your population is probably some age range of children. If you're a cognitive psychologist and you deal with what are just considered adults, you're probably dealing with people that are 18 to 50. If you are a cognitive psychologist who deals with aging, then your population will probably be what are considered older adults, 60 and above. Okay, so the population is whatever it is that you are studying in general. So that's everybody out there. But of course, all we can do when we do research is take a sample. Right? We take some sample of that population. These are the scores that we observe, and then we use the scores on that sample to estimate characteristics of the population. Again, that's the inferential game that we play. So the population and the sample are two very important distributions that we deal with in statistics. You might remember this, another very important distribution that we deal with is, get this, so for a meta distribution. It's a distribution of sample distributions, okay? Now this is getting pretty deep into statistics, but remember, the idea is if I say I'm going to take a sample of size 30, okay? I'm going to take a sample of size 30, so 30 individuals, and I'm going to measure them somehow. I'm going to compute a mean, and then I've got a mean that's equal to this, and I want to know how surprised am I by that set of data? Well, I've got to have something to compare it to, right? So what do I compare it to? Do I compare it to the population? Oh, I don't know the population. Do I compare it to the sample? Well, no, it is the sample, right? What do I compare it to? What I compare it to is a distribution of things like it. Well, what was it? A sample of size 30, right? So I've got to somehow construct a distribution or collection of samples of size 30. It's literally a distribution of sample distributions. And so when you start dealing with Z distributions and something called standard error, or T distributions, which are very similar except for one small thing, or F distributions, remember F for Fisher with ANOVA, those are, yeah, not Faulkenberry, right? We established that in class. Those are sampling distributions. Those are distributions that arise from taking samples of a given characteristic, of a given size. And so again, everything we do in our statistics study is all about looking at specific types of distributions. So distributions are king here, okay? So you want to keep those definitions in mind for sure. And just so you know, there's a lot of stuff that you're going to see that you're not going to be able to write down today, but Dr. Robertson has a copy of this PDF, 2 slides per page, so she'll make that available to you. Real quick review, how do we describe distributions? So if we want to describe things and we want to infer from things, let's talk about the descriptive part first. How do we describe distributions? There are many different ways. The 2 main things that we consider, however, if you think about this, this shows up everywhere, whether it's in statistics or in research, is we talk about describing the center of the distribution. So that's kind of where most of the data is. Usually, without even thinking about it, we use the mean as our center. Sometimes the median is a better measure. Sometimes the mode is a better measure. It all depends on the type of data that you're dealing with. If you're dealing with continuous or so-called interval or ratio scale data, then means are usually pretty good, unless you have a lot of skew. That's a different story. If you're dealing with non-interval scaled data, so something like ordinal data, the median is a good one to use. If you're dealing with nominal data, things like gender, hair color, things that there's no order between them, they're just different labels, then mode is one of the best measures of center. Again, regardless of which of these 3 measures of center, the purpose of that measure is to describe where the data is. What does most of the data look like? What is the most reflective thing that reflects this distribution? The most informative thing that reflects this distribution. So you got your measures of center. But you've also got measures of spread. So everyone's favorite, the standard deviation or variance. If you remember, if you took the class with me, the way we looked at standard deviation was we simply defined it as how far on average data points are from the mean. Okay? Now, a good way to visualize what standard deviation is, of course, is to look at the difference between something that has a very small standard deviation or low variability versus something that has a high variability or a large standard deviation. Let's just do a quick example. Whenever I give an exam back, I'll tell you guys, the mean was, say, 70. And then I'll say the standard deviation. And besides the fact that I'm just a little touched in the head like that, I like to give you standard deviation because here's what it tells you. If I tell you the standard deviation is 10, then that tells you that on average, each person is about 10 points away from that mean of 70. Now, some people are going to be right on it. Some people are going to be beyond 10 points away from the mean. But on average, the spread away from the mean is a spread of 10 points. So that's what standard deviation essentially tells you. Right? So again, standard deviation, regardless of if you remember how to compute it, which again, I don't believe the Major Field Achievement Test will actually ask you to do this, know what it is. It is a measure of variability or a measure of spread. Right? Okay, now from these 2 descriptive statistics, from the mean and standard deviation, we get possibly one of the most useful formulas. And yes, this is one I'll actually ask you to look at. One of the most, possibly one of the most useful formulas and concepts in statistics. And that's the notion of a z-score. Raise your hand if you remember z-scores to any extent. Look at that, it's got some z-scores. Now some of you didn't raise your hands, I'm a little worried about that. We talked about it a lot. So what is a z-score? A z-score is, I don't care what it says up here, I'll tell you what I'm thinking right now. A z-score is essentially nothing more than a way to locate where specific scores are in a distribution. Okay? So formulaically, that's what it is. If I tell you you've got a z-score of 1, that has a meaning. That tells me that I am somewhere above the mean. Okay? If I have a z-score of -1, that tells me I'm specifically somewhere, but because of the negative, that means I'm below the mean. And how much? Exactly 1 unit of something. Does anyone remember what that 1 means in a z-score? So if I say I've got a z-score of 1, what does that mean? I'm very sad right now. I just had these guys in stats last semester. No, just think about this. So if we'll see in just a second. But if I tell you got a z-score of 1, this person's got a z-score of 2, what's the difference between those two people?
Is it one standard deviation?
That's exactly what it is. Yeah, thank you, Andrea. That's nice. Yes, it's exactly 1 standard deviation above the mean, or 2 standard deviations above the mean. A z-score tells you where you are in terms of 2 things: the center, the mean, and the standard deviation. Right? So if you remember, the formula for a z-score is pretty simple. It is a formula that you used structurally all semester in your stats course, right? Because z-scores look like this, t-scores look like this. Just about everything that we did all semester long involved a computation that was something like this. The x minus mu part, that's literally this distance between the data point and the mean, okay? It's a raw distance, if you will. When you divide by sigma, the standard deviation, you're taking whatever that raw distance is and you're scaling it down to be in terms of standard deviation, okay? So now, whenever you have a distribution like this, we're going to use this example for a couple here. Let's say we've got a normal distribution that has a mean of 100, so that's its center, and a standard deviation of 50, okay? So that standard deviation tells you kind of how spread out it is. Then the z-score is going to tell us a few things. Let's see exactly what it tells us. First of all, let's look at a raw score of 100, okay? So if you have a raw score of 100, the question is, what does that transform to as a z-score? Well, we can easily do this if we remember the formula. The formula for a z-score is the raw score x minus the mean over sigma. The mean is given to us. What was it again? Well, sorry, yeah, 100. And what was the standard deviation sigma? 50, right? So now if we just plug in a raw score of 100 into this formula, we get 100 minus 100 over 50. Do the 100 minus 100 first, you get a 0. So this z-score turns out to be exactly 0. Right? What that means is that for any distribution, the mean itself, the whatever score is at the mean, has a z-score of what? 0. What does that mean? That means that the mean, too many means here. This represents the fact that the mean is 0 standard deviations away from the mean. Right? You are no distance from yourself is basically what that says, right? So that's anytime you have a mean, the z-score is 0. Okay. Now let's take another example here. Let's look at 150. I very specifically chose this example to illustrate another concept. So again, let's take a raw score of 150. Here it is. Okay, right? It's going to be to the right of whatever the mean is. Plug that into my formula. My raw score is 150 minus 100 over 50. Now what does this top turn out to be? 50. 50 over 50 is 1. This means that a raw score of 150 has a z-score of 1. Well, why? Because remember, a z-score counts the standard deviations that you are away from the mean. What's the standard deviation in this example again? 50. If your mean's 100 and you're at 150, how many standard deviations are there in this distance? Exactly 1, right? So that means that 150 has a z-score of +1. You can do the exact same thing with 50. 50 is going to be 50 units to the left. Well, each standard deviation is 50 units. So over here to the left, you've got a z-score now of -1. So z-scores are important because they take, here's the thing, they take any distribution that you start with, regardless of what its mean is, regardless of what its standard deviation is, and they transform it into a distribution that looks like this. with mean 0 and standard deviation 1. Okay. Why is that important? Well, let's just suppose, I'm gonna riff on an example that I use when I'm teaching stats. Let's suppose that you've got some students and you measure their math aptitude via a certain instrument. And then you measure their reading aptitude by a different assessment. So these assessments all have different scores, etc. So, you know, they make a 50 on the reading assessment and a 6 on the math assessment. Which subject are they better in? I want somebody to answer quickly. Oh, exactly. Yeah, I'm thinking too hard about this. You're absolutely right that you need more information, because just because there's a score of 50 on one exam, math, and a score of, or maybe I think I said reading on that one. Reading was 50 and math was 6. Just because you have those raw score differences doesn't mean anything, because they're on different scales. The distributions of scores for each test is different. What's the mean reading score? Suppose it's 45, you know. Does that tell me anything? Well, I now know this person's a little bit above the mean. What's the mean score on the math? Well, I don't know. Let's say it's 10. Now they're a little bit below the mean. The whole point is you can now, if you convert each score from a raw score into a z-score, you can now say with a nice comparison, this person is better at reading than math, because in reading, there's some number of points above standard deviation, whereas in math, there's some number of points below the mean. Okay? I think I said standard deviation a second ago, I meant mean. But the idea is if you put everybody on the same distribution, namely this z distribution, then you can compare them. Now, I'm spending a lot of time on this because this concept shows up quite a bit on the major field test. Okay? It is foundational to our discipline. Okay? So z-scores represent a standardization, if you will, of any raw scores. This is why whenever you get a table in the back of your stats book, or if I give you a table in class, it's called the standard normal distribution. That's a distribution, a single distribution that is centered at 0 and has units of spread exactly 1 unit. Those are z-scores. Okay? And you might say, well, Dr. Faulkenberry, this doesn't work for any of the data I collect. I deal with intelligence testing, and IQ measures have a mean of 100 and a standard deviation of 15 or 16, depending on the norm of the test. And I'm going to say, that's great. Take those scores and convert them to what? Z-scores. If you do that, then you are on the exact same distribution that I use for reaction time measures. The idea is that every single raw score distribution can be converted to a z-score distribution. And what's more, some of them turn out to be exactly like this. Not all of them, but some of them turn out to be exactly what we call a normal distribution. So that moves us kind of on to the next little part. You guys have any questions that I can stop and take a drink of coffee for, possibly answer before that?
I'll just add too that understanding this concept, understanding mean, standard deviation is really important in figuring out how to calculate your score, how I'm going to convert your score on the major field test to your grade in this class, right? Because that major field test is worth 25 points. But you're going to get a score back that's going to be like 472, right? And so I'm going to have to do a score conversion, and I'll be using these statistical measures to make that score conversion to give you your grade on your major field test so that you get a certain number of points.
She might make you do it too, so just...
That's a great idea. I love that.
How many points do you want? Yeah. So, yeah, that's a great point. I mean, this underlies, I mean, I don't care if you're going into research or if you're going into an applied measurement type field. This is absolutely one of the things.
Or clinical.
Absolutely.
I use it all the time.
Absolutely. Well, let's talk a little bit about normal distributions. Now, whenever I teach stats, I always have to give you a little bit more than what the picture is in the textbook. You know, a lot of times textbooks will present the normal distribution as this magical thing that all humans turn out to be normally distributed, and that's such BS, okay? There are very few things in life that are normally distributed. What we're hiding there is the fact that when you take large enough samples of humans and then measure them, the means of those samples turn out to be normally distributed. That's something called the central limit theorem. So studying normal distribution is a very important concept. Not because the distributions themselves, the raw scores, turn out to be normal all the time. It's because the distributions of samples do. Okay, it's just a mathematical fact. So normal distributions are pretty cool. They're pretty cool because of several things. One, they're symmetric. Okay, and so if you know things about the positive side of the distribution, you know the exact same thing about the negative side of the distribution. Okay? For example, you know that exactly half of the curve is above the mean. Okay? Another way to look at that is if you say, what's the probability that my z-score is 0 or bigger? Right? Well, it's this area under here, which is exactly 50%. Again, because this is a perfectly symmetric distribution. The same exact idea can be used to answer things on this side. What's more is we know certain percentages of being within a certain standard deviation of the mean or not. So for example, what's the probability that my randomly selected participant will be 1 standard deviation above all the way down to 1 standard deviation below, between a z-score of -1 and 1? Does anyone remember the answer to that? I'm gonna stop asking that question. That's exactly it. Yeah. So you can answer all these questions by remembering this key rule. It's called the 50-34-14 rule. That is made to represent basically 3 benchmark numbers. If you can remember those, you can remember just about everything you need to know about the normal distribution in terms of area under the curve. Okay. So, for example, where does the 50 come from? Yeah, that's the whole half, right? We just did that one, right? So it's this exact whole half. And again, because it's symmetric, the exact same picture could be overlaid on the left side as well. The 34, where do you see that one coming up? That's right here. The area under the curve, or the proportion under the curve, if you will, between the mean and 1 standard deviation is right about 34%. It's exactly 30, well, it's not exactly, it's really close to 34.13%. Again, just remember the 34. This is about 34% of the curve. So if I asked you what's the proportion between 1 standard deviation below and 1 standard deviation above, what would that be? 68%. You got 34 here, 34 here. Okay. Now if you extend this out, so there's your 68%. If you extend this out to 2 standard deviations on each side, you get 95% of the curve. This is important because this number comes up all of the time. All right? If you remember anything about hypothesis testing, which we're about to recover here in just a second, you remember that you had to get z-scores and t-scores that were 2 or bigger. All right? Z-scores need to be 1.96 or bigger. T-scores depend on the size of the sample, but in general they need to be around 2 or bigger. The reason is because once you get 2 standard deviations from the mean, you're out here in these sort of exceptional regions, or these tail regions. You are surprising, and that's what we mean when we reject a hypothesis test. When we reject a null hypothesis, we mean that data is pretty darn surprising. That means it's out here in the toilet. So remember, again, the reason I'm presenting this is not just to say, hey, look at all the stuff you used to know, okay? These are the kinds of questions you will see. Okay? I can almost guarantee you in some form. So try to remember those kind of benchmarks about the normal distribution. So again, the rule is 50, 34, 14. 50 all over the half, 34 in the first sector, about 14 in the second sector. Okay. Let's change gears slightly. That was all about descriptive statistics, describing data, okay? Describing things in terms of the center and standard deviation, describing things in terms of where it's located, where a raw point is located within the distribution. Now I want to talk a bit more philosophical, okay? And it requires a bit of suspension of belief. All of you have gone through the process of hypothesis testing, and regardless of the extent to which you remember the specifics, you probably remember some weird stuff going on in hypothesis testing. So my goal right now is to remind you of that weird stuff. and to walk you through the logic one more time so that you remember what is this game that we do when we do research. What is this whole thing about null hypotheses and rejecting them? So I want to start as an example of our inferential statistics with a typical example. And because I do like memory, I'm going to use a memory example. So again, the purpose of inferential statistics is to take a sample and use that sample to make a claim about the population. You infer up to the population. So let's do a little experiment. We got two groups of participants, A and B. In Group A gets some sort of treatment that's supposed to improve their memory. You can use your imagination as to what the treatment is. This is your example as much as it is mine. The point is they get some treatment. Group B gets no treatment, or you can think of it as a placebo or whatever. And then what I want to do is test, is there a difference in memory between these two groups? So after the treatment period, I test both groups on a memory measure and I get the following results. Group A, they get a memory score, whatever that is, of 80%. Group B gets a memory score of 76%. Do we write to the New York Times and say, we have figured out how to reverse memory loss? Well, we got some work to do first, right? So we got a difference, 4%. What we don't know from this data as it is presented is whether that 4% difference is a real difference. I put real in quotes because what is real, right? What we mean here is it statistically significant? Or is that 4% just sampling error or measurement error or any number of sources of error when we measure humans? The fact is, from this description alone, we don't know. This is why we spend 2/3 of our stats course talking about hypothesis tests, because then that gives us some tools, some machinery, if you will, to be able to assess a question like this, where we take this descriptive data and then try to infer something from that descriptive data. Right, so that's our game, and let's now try to remember how this works. Okay? How do you test hypotheses? Look in any stats textbook, you'll see anywhere from 2 to 10 steps on how to test hypotheses. And they're all probably correct. There is no fixed number of steps in doing hypothesis testing. I like to present it as the following 5 steps. This is probably different than the way I presented it to you in your class. The point is, you can basically boil it down to something like this, depending on how much coffee you have ingested before writing the lecture. So we're going to do it as a 5-stepper today. Don't remember the steps, remember the overall thing. First step is to state your hypotheses. So we typically do that in terms of 2 different hypotheses, a null hypothesis, which we'll cover in a second, and an alternative hypothesis. We set our decision criteria. In a sense, that will tell us how big does the difference need to be before we decide, yeah, this is a real difference. So this is something called an alpha level that we'll review in a second. We collect data, that's the easy part. We then compute some test statistics, that's the easy part. Especially since now that you're through your stats course, you just use some software to do it. Okay. Those of you that have had research know that's exactly what we do. Those of you that are in research, that's what we're going to do. Okay. And then finally, number 5, once we've computed those test statistics, those statistics allow us to make a decision about the null hypothesis. And our decision typically comes down to 2 alternatives. We either reject the null hypothesis or we fail to reject the null hypothesis. If at any point you wanted to use the verb accept as an alternative to reject, I want you to squash that tendency from your vocabulary forever. Okay. Explain why in just a moment. So this is hypothesis testing. Let's look at these steps in a bit more detail. Step 1, state your hypothesis. So again, we typically do this by pitting 2 competing, logically opposite hypotheses against each other. We set the null hypothesis and then the opposite of that, the alternative hypothesis. Now what usually happens is that we are interested in the alternative hypothesis. But the way the testing works you can't get support for that hypothesis directly. What you have to do is set up a weird situation. Let me try to outline the situation for you. Remember our memory example. We're interested in whether group A is bigger than group B. So we got some data. Does that data give us evidence that group A is bigger than group B? Well, unfortunately, no. But what it can give us evidence for is a little different. It can give us evidence, follow me, that it is not the case that there is no difference. Say that again. It can give us evidence that it is not the case that there is no difference. In other words, what we are saying, and forgive the horrible grammar for a second, is we are going to say that there is not no difference. Okay? And it is perfectly fine to say that in this context, because when we say, hey, let's set up a null hypothesis, that's a hypothesis of no difference. Now, let's collect some data. Oh, look at this data. There's a difference of 4% there. That's surprising if there's no difference. In fact, this is so surprising that I reject that original hypothesis of no difference. So I'm going to say that my data gives me evidence that there is not no difference. Kind of weird, isn't it? Take it up with Jerzy Neiman and Pearson and all those folks back in the early 20th century. But that's how it works. That is the so-called null hypothesis testing framework. We set up a hypothesis of no difference, the null hypothesis. That's again logically opposite from the one we're interested in. And then what we try to do is not get support for the alternative, but instead we try to reject the null hypothesis. And if our data rejects the null, that leaves us with support for the alternative hypothesis. So essentially, we get there in the end, but through the back door. It's double negative logic. Okay? So that's how it works. Just literally say there's not no difference. So in our memory example, the null hypothesis here would be, again, the hypothesis of no difference. So in this case, we would say that the mean of group A was the same as the mean of group B. That's a typical null hypothesis. Then, of course, our alternative is going to be whatever is logically opposite from that. The opposite of equal to is not equal to. Right? So the alternative hypothesis is that the mean of group A is not equal to the mean of group B. Now, sometimes we do what's called a directional hypothesis, and that leads to the concept of a one-tailed versus two-tailed test. That's a very specific thing from statistics that I won't go over today, but there's the idea. And so then what we do is we test this claim, not through testing the alternative, but by testing the null. That means we suppose the null, that gives us a distribution that we would expect, and then we compare our test statistic to that distribution. And if it's out in that tail, that means it's relatively rare. That means it's very surprising given the null hypothesis. So it could not be the case that that null hypothesis was even true to begin with. And if the null is not true, then what has to be true? The other one. Right? So that's how it goes. You reject the null to get support for the alternative. So that's why step one takes a while. Now, step two, we set our decision criteria. Decision criteria is essentially how surprising does the result need to be? How big does the difference need to be before we reject the null? What level of evidence do we seek in order to say, yeah, this couldn't have come from a null distribution? Okay? And so what we do is we set something called the alpha level. Okay? And usually we set alpha to a very specific number. Does anyone remember what that number is? It's 0.05. That's the magic. If your p-value on your test, those of you that have done research, you got the p-values from your software, when the p-value is less than 0.05, you're happy. Right, because it's less than 0.05. It's less than this decision level. Now, where does all that come from? What it comes from is the fact that when you do a hypothesis test, there are a couple of ways you can screw it up. And they're called type 1 and type 2 errors. And again, this is one of those big concepts from stats and research that we need to cover. So I'm going to go back into some discussion about what we mean by type 1 and type 2 errors. Okay. So you may have seen this diagram in my stats class. I like to use it over and over again. Here's the idea. So let's look at kind of two possibilities pitted against each other. In the real world, there are two possible truths. Now, I don't know what these truths are, but there's two possibles. Either the null is correct, there's no difference, or the null is wrong. There is a difference. It's the only two possibilities if you think about it that way. Now, it doesn't say anything about the relative likelihood of each of those, right? That's the same kind of thing as explaining, well, it's either going to rain or it's not, so it's 50% chance of rain. Right? That's not how it works, right? On a day where it's really cloudy and there's a lot of moisture in the air, it's a lot more probable that you're going to get rain. Even though there's only two possible outcomes, they're not equally likely, right? So yes, it is absolutely okay to divide the world into these two possibilities. One may be way more likely than the other, but that's irrelevant for now. So you got those two possibilities for the real world truth. But see, we can't play God here, right? We don't know what the truth is. All we know is what we observe, what we do from our test. And our two possibilities when we do a statistical test are to either reject the null or what? Not reject the null. Not accept, right? We either reject or fail to reject. Those are our two possibilities. Now the question is, given the two possible truths and given the two possible actions that we can do as researchers, when are we right and when are we wrong? Right? Well, we're right exactly 2 times. Okay, those are the smiley faces. Let's focus on those first. I like to focus on the positive. Okay? If we reject the null, we're correct if the null was incorrect, right? You want to reject the wrong null hypothesis. So if the null is incorrect, if there really is a difference between the two groups, and we reject the null, we are absolutely right. We're also right if we fail to reject the null if it's correct. Right? If the null hypothesis is true, you don't want to reject it, because it's true. So we're right in these two instances. If we're right in those two instances, though, that means we're wrong in the other two instances. So let's look at those errors. Let's focus on this one first. The null turns out to be correct, but we reject it. Okay? That's called a type 1 error. It's also called a false positive. Okay? What we are essentially saying is that if by rejecting the null, we're saying there's a difference. There's a difference between the groups. There's an effect, but there's really not one. So we're claiming there's an effect when there's really not one there. We're claiming that this memory treatment has an effect when it really doesn't. We're claiming that this drug does this certain magical thing when it really doesn't. Okay? That's a type 1 error. This symbol alpha here refers to the fact that by that alpha level that we were talking about, that's literally the probability of making that kind of an error. When we set alpha at 5%, we are controlling, just by our very experimental design, we are controlling the probability of making one of those type 1 errors. So whenever we do an experiment or we do a study and we set alpha equal 0.05 from the outset and we make a decision, we don't know if it was the right decision or not, but we're 95% confident that it was the correct one. Why only 95? Because there's a 5% chance that I've made one of these. That I've made one of these type 1 errors. So it's a give and take, right? We don't know anything with absolute certainty. Go into mathematics if you want that. In empiricism and in any empirical science, we have to deal with likelihoods, with probabilities, and that's as good as we can do. So when we set our decision criteria, what we're literally doing is controlling for the type 1 error rate with that alpha level. Right? If you set alpha at 0.01, right, that's a little smaller. That means you've got to have an even bigger difference. Because you think about it, 5% in the tail happens at z-scores of 2. That means you got 95% of the curve between -2 and 2, and you got 5% in the tail. If you want only 1% in the tails, you got to go even farther out here to like 2.33 on each side. Okay? So you've got to have an even bigger difference to reject something at the 0.01 level. But the benefit of doing that is by making it a more stringent decision, you're more confident in your decision. You're now 99% confident that you've made the correct decision. There's only a 1% probability that you're making a type 1 error. Okay? So that's what this is all about. It's all about error control. Right? Since we don't know whether we're getting it right or wrong, we need to just try to minimize our errors as much as possible. Does that make sense? That's the idea. Okay? That's why we do what we do. Okay? That's one type of error. The other type of error gets a different name because it's a different type of error. Again, we're wrong. Why are we wrong? We're wrong because we failed to reject the null when it was a wrong hypothesis. So if the null is incorrect, that means there is a difference between the groups. But by failing to reject, that means we didn't find it. So that's called a false negative. We say there's no difference between them when there really is. You just didn't find it. You didn't look hard enough. You didn't get a big enough sample. You didn't detect the difference. Okay, so that's what that's all about. So that's a fundamentally different type of error. And we call that a type 2 error, or false negative. Yes, ma'am?
So if you run your alpha at 0.05,
yeah.
and then can you go back and run it at 0.01 to be even more sure if you're really sure the first one? Like if you really want to prove your study.
Right. Yeah, so it's a complicated answer to your question. You essentially get that for free when you do the hypothesis test, because the way we do our hypothesis test gives us the p-value, and the p-value is literally the probability of making that type 1 error. And so if we get a p-value that's 0.001, then we're not only rejecting it at 0.05, because it's less than 0.05, we're also rejecting it at the same time at 0.01. So in a sense, we're getting a measure of evidence with that p-value. So not only are we rejecting, but we're knowing by how far as well. Now the problem there, and this is all philosophical and need not concern you past this unless you're just interested in, is that we are sort of incorrectly mixing two fundamental ideas from the early 20th century. There was Fisher's notion of p-values, and then there was Nyman Pearson's notion of rejecting the null hypothesis. And they're fundamentally different. And if you combine them, you actually get mathematical impossibilities. But unfortunately, that's how every behavioral statistics course has ever been taught for the past 50 years, is combining them. So the stuff I'm saying to you, if you follow it down the rabbit hole enough, you'll actually wind up with some BS somewhere. But in all practical purposes, again, sort of at the real world level, it's okay, right? So that's why I said it's a really long, complicated answer. But in a sense, yes. Okay, so hopefully that helps. Okay. I like to be transparent, but sometimes a little too transparent. Okay. So everything we've taught you is wrong. It's not true. It's just subtle. Okay, that's all it is. So type 1 errors we talked about there. That was a great question. Type 2 errors are a little different. Again, you're saying there's no effect when there really is one. So that gets its own symbol, beta. Okay, and beta is the type 2 error rate. Now the question is, how do you minimize that? You minimize this one by setting your decision criteria. This one is related to something called statistical power. And it's not something that we cover a lot in the undergraduate curriculum other than the what it is, because computing power is extremely difficult, even for just very simple situations. And if you have a more complex design with multiple independent variables, it's mind-blowing. You really need some software for it. So you sort of get that more at the graduate level. But the idea is that power is the probability that you're not doing this. So you really want a lot of power in your test. Power is the probability that you'll detect effects when they're really there. So you want a lot of power. Would you rather use a cheap microscope or a really high-powered microscope, right? You want to see stuff. You want to really detect it. If you're going to spend all this time and all this human capital that you're talking about when doing research, you want a high-powered test. And so that's how we minimize type 2 error, is by ensuring sufficient power. And if you'll remember, you can do that by having a big enough sample, making sure you use the right test, having good protocols in your experiments, etc. Okay. So again, this little slide I'm not going to go through because we've already talked about it, but on your handout you'll have it and all that good stuff. Step 4, step 3, you collect the data, boom, do it. Okay. Step 4, compute your test statistics. You do your descriptives, you do your inferentials. That's where your t-test comes in, or your ANOVAs. We'll review what those are for and when you use them in a second. And then finally, you make a decision about your null hypothesis. If you reject the null, you're saying that there is a statistically significant difference. If you fail to reject the null, you're saying there's no statistically significant difference. And that's the game. And if you remember in stats, we always get really excited when this happens. And in research, we get really excited when this happens as well, okay? So it doesn't just stop in your junior level stats course. I do want to briefly bring up the following question. So what is statistical significance? This is a very, very misunderstood concept many times. So what happens when you reject your null hypothesis? I'm not going to focus on all the things that are incorrect. I don't want to put those in your head right now. I want to just focus on what it really means. Okay? What it means is that your observed difference is above what you would expect by chance alone. Again, remember the whole idea of measurement error being basically a random chance type thing. Sometimes you're going to be above, sometimes you're going to be below. We want to know that our observed difference is beyond all that, beyond the noise. We want signal. We don't want just a bunch of noise. Question is, how do you determine chance? And the answer is you estimate sampling error. And that's where these sampling distributions that we talked about came in. Remember the concept of standard error, where you take the standard deviation and divide by the square root of the sample size. Those are estimates of chance, essentially. And once you get those estimates of chance, then you get a nice test statistic that will let you compute whether your difference is above what you would expect by chance alone. So that's how all this fits together into a big philosophical framework. When you say you have a statistically significant difference, you're saying there's a difference above and beyond chance, but you're also saying that there is a probability of 5% that the researcher has made a type 1 error. So there is a big difference between statistical and theoretical significance. Statistically significant does not mean true. Statistically significant does not mean proof. It means it's a little bit bigger difference than I would expect. Now again, the smaller the p-value, the smaller this percentage becomes, and the more confident we tend to become in our estimates. But it's not proof. Never, ever, ever, never, ever, and if you have, never again, use the word prove in the context of empirical science, whether it's your discipline or any other empirical science. In fact, think about it this way. If you want to use the word prove, you better be doing logic or mathematics, because proof has no place elsewhere. It's all evidence. It's all support. Okay? Real quick, suppose you're doing research, and those of you that are going to go into grad school and do some research, sometimes this is kind of like the Dr. Seuss book, right? Sometimes you'll win, sometimes you won't. I can't remember the exact words right now, but sometimes what happens when you don't reject the null, you fail to reject the null? Remember, you can't accept a null hypothesis. So because you didn't find a difference, that doesn't mean there's no difference, unless you're Bayesian. That's a different course. The way we do this with this null hypothesis framework, you are left with basically nothing. But what you need to do is check to see if you made a type 2 error. Make sure that when you say, well, I didn't find a difference, make sure it's because your study is not underpowered. Your study's underpowered. Maybe there is a difference, you just didn't find it. That's not a situation you want to be in. You want to be in a situation like, by God, if there was a difference, I should have found it, because I've got a study with 95% power. Right? That's actually a pretty good argument that you can make in the discussion section of a research paper. Okay, I'm going to finish up. We've got probably about 10 minutes to go through a couple of things here. I want to briefly cover what statistical tests look like and then review the common ones. Oddly enough, I know on the sample that I saw of the major field test, there weren't a lot of real specific questions about statistical tests other than maybe when would you use this one versus not. So remember, any statistical test needs to basically analyze variability between groups. But you've got a lot of sources of variability. You got sampling error, you got individual differences, people always worry about that. And then you've got the one you're interested in, right? The treatment effect. You want to know, does this memory treatment have an effect? So you want to kind of maximize that one and cancel out all the other ones. So one way you can do that is a very simple fraction where you essentially put the observed difference, remember x minus mu, Remember the z-score? That's exactly what that is. That's an observed difference divided by the difference from chance. Sigma? That's what that is. It's the difference by chance, right? So when you construct a z-score, you're essentially constructing a test statistic. And if you move to a t-test, you're doing the exact same thing. If you move to an ANOVA, you're doing exactly the same thing. If you move to something called a chi-square, you're doing exactly the same thing. Regardless of the actual formula, what you are doing is comparing the observed difference to the difference that you expect from chance. And if that's big enough, then you're saying, I'm getting a difference of what? Beyond what I would expect by chance alone. That's how these test statistics work. You take those sample means, turn them into the test statistic you're interested in. So z-scores look like this. T-scores look like this, a little fatter in the tail. F-scores look like that. Chi-squares look like that. You get a distribution of test statistics. When you set your alpha level, it tells you how far out you need to go to reject. The whole game comes together regardless of the distribution you're using, whether it's Z, T, F, chi-squared, any of the non-parametrics later, these things all fit together under the same framework. If you are inside this with your test statistic, it's not big enough, then you fail to reject. If you're out here in the tails, you reject. End of story. Let's real quickly remember when you use what, and then we'll end up with a little bit of discussion of some non-experimental stuff. Whenever you have a single independent variable, remember the thing you're manipulating, whenever you have a single independent variable with two groups, that's a t-test situation. Okay? Now again, this is assuming that you're measuring something continuous, like a test score or a time to complete a task. You're not just doing counts and stuff. You're measuring a continuous dependent variable. Then whenever you have that single independent variable with two groups, that's a t-test situation. It's either an independent samples t-test or a paired samples t-test. When do you use which one? Well, it depends on this verbiage right here, between subjects versus within subjects design. I can very quickly illustrate the difference between those. I'm going to do a test. I'm going to do a test on a memory treatment, and I'm going to give this half of the room, those of you that have me in learning in this room know I do this all the time, this half of the room gets the memory treatment, this half of the room gets a placebo. That's a between subjects design. That means literally I am manipulating the variable between these two different groups of participants. Okay. But if on the other hand, I said I'm going to take all of you and I'm going to give you a pretest, and then about a month later I'm going to give you a post-test, then I'm manipulating that variable within each of you. Each of you is getting multiple levels of that independent variable. You're each getting both occasions of that independent variable. So in that case, that's called a within subjects design. And we use what's called a paired samples t-test. Sometimes it's called dependent means t-test. You see it in a lot of different ways. But independent samples literally means the two samples are independent of each other. They are not the same people. Dependent means or paired samples t-test, they're all the same people on multiple occasions. The key is whenever you have two groups, that's a t-test situation. If you have more than two groups, what do you have to use? ANOVA. Yeah, that's where the ANOVA or analysis of variance comes. So if you've got the single independent variable with more than two groups, it could be 3, 4, 5, 10, whatever, you're going to use your analysis of variance. It can also be either within or between subjects, although we never cover the within subjects part of this in our stats course, but you can't do that. One of the things that we rarely get to, unfortunately, but it is important to know what it is if you have a single independent variable, but you have a categorical dependent variable. So like you've got, demographic breakdown as a function of campus. Okay, what if you were interested to see, is the Fort Worth campus demographically different from the Stephenville campus? So what are those data? They're not continuous data, right? They're counts or they're proportions, if you will. And with that categorical data, a t-test doesn't work at all. Okay, it doesn't meet the assumptions of a t-test. So you can use something called a chi-square to do this. And again, just know what it is, and you might just want to look that up sometime this semester just to see, what is a chi-square. If you still got your stats book, it'll be in there, okay? It's one of those things at the end that I never get to, okay? If you had it with a different person, then potentially maybe you got there. Okay. Let's end up 5 minutes. Will that be enough time at the end for the questions? Okay. Let's end up with a real quick go through of certain non-experimental designs. Those of you that are in research right now will not have gotten to this because it's typically at the end of the semester, at least for my course. Why do we call it experimental versus non-experimental? The key is that in any experiment, you have random assignment. What random assignment, so like you got your two groups, A and B, so what I just did a second ago is totally not a real experiment because I didn't do random assignment, right? I just say, oh, you're sitting over here, I'm gonna take that, right? You're sitting over here, you're gonna be a group. The problem is there might be a tendency in all these people over here that makes them choose this side of the room that I'm not then controlling, okay? And so everybody usually, when they start doing experiments, has a question, oh my God, how do I handle all of the individual variation? How do I cancel out all the individual differences? And the answer is if you have your groups, randomly assign to those groups. That random assignment then makes it mathematically the case that all those individual differences average out in the individual groups. So there's no mean difference between the groups in anything except potentially the manipulated variable. So random assignment is the key. So what that means then is if you don't do random assignment, you are not doing an experiment. So anything that doesn't have pure randomly assigned groups is then called a non-experimental design, even though sometimes we still call them experiments. You get things like quasi-experiments, developmental designs, small n designs. And I want to put a note here. I always say this so that I remember, I'm an experimental psychologist. Sometimes people think if it's non-experimental, I'm not going to like it. That's not true. Non-experimental does not mean bad design. It just means it doesn't have random assignment. It's got some things you got to take care of. Okay? So what is a quasi-experiment? Definition is an experimental design with no random assignment. So it's not experimental, but it's sort of the same thing. It's quasi-experiment. Usually, whenever you're interested in things like time, pre-test versus post-test, you can't randomly assign time. I can't randomly assign you to take this one first and then last, right? I can't manipulate time that way. So time, I've got to just let it happen as it does. And so, if you're interested in males versus females, I can't randomly assign you to a male or female group. It just doesn't work that way, right? So when you can't do that, you've got a non-experimental design. I'm gonna skip over some stuff here, but basically, you've got your typical pre-test, post-test design. That's an example of a quasi-experiment. There are some things you have to take care of. You have to make sure that you're not dealing with history effects, or just maturation. When you see an increase from pre-test to post-test, how do you know it's not just because kids are getting older, or something like that? How do you know it's just not the effect of maturity that's causing the test differences? So there are ways to eliminate these as potential explanations. Right? You get more and more complex designs as you go. You're probably not going to get into this much detail for the achievement test, so I'll leave it here as reference for you when you get your handout. Just for fun, read up on the Solomon 4 group design because, it's cool to bring to like a pub sometime and have a conversation. Hey, let's do a Solomon 4 group design. What is that? Well, now you know, right? So take a read on that. Developmental designs. These are, whenever you take your developmental psychology courses, anything that deals with lifespan or child psych, there's a lot of these, right? Because you're interested in how mental processes, how behaviors change over time in a person, right? So what are those developmental changes? And there are typically two major types of these developmental designs that we talk about. We've got cross-sectional versus longitudinal. Big difference between them. Cross-sectional is where you essentially use age as a between subjects variable. That means right now, at this one time, I take all the 10-year-olds and all the 12-year-olds and all the 14-year-olds and I compare them. Okay? So as a cross-section of the population as it exists right now. Okay? So essentially, diagrammatically, you've got these then getting one test. The nice thing about a cross-sectional design is you don't have to follow them. Right? You take all the differences right now. But the problem is, you get a lot of data at one time, but you're not following those individuals over time, and so anything you see might be what we call a cohort effect. You know, if I'm looking at cell phone behaviors in 10 versus 12 versus 14-year-olds right now, I mean, how do I know that's anything due to development? It's not just due to something about the state of the times that we're in as it is right now. Okay? So if you really want to see how those behaviors change over time in an individual, you have to do something called a longitudinal design, which is where you take a group of people at a certain age and then you follow them 4 years or however many years later into this age, and then you follow them later. So of course so at this case, age is a within subjects variable, right? We're taking a person and testing them at this age, and then at this age, and then at this age, right? We're manipulating time within that person. What's the major problem with longitudinal designs? Well, there is that. You have people can drop out at any point for various reasons. Would you, so let's say you're going to do a master's degree and you want to be done in 2 years. Do you want to do a 5-year longitudinal study on someone then? Better not, because it's going to take you how long to collect the data? 5 years, right? You have to follow them through time. And so time is a major disadvantage here, but it does give you much more of a clear picture on developmental changes. Major thing, and again, here's some of those attrition and mortality that you just mentioned, history, practice effects. These are all possible disadvantages to developmental designs as well. In all of these, you still can't determine causality. Okay? Again, causality comes when you are able to manipulate an independent variable via random assignment. That's an experiment. That's what experiments are for. That's what we use them for. In all of these, you've always got the possibility of lurking variables, or what we call confounds, that can muddy up the interpretation. Doesn't mean that the findings are any less valid. It's just that you have to consider them with the cautions that you get presented with. I'm going to skip over that, and we're going to be done right now. Okay. So again, I've put a lot of stuff on the handout. You guys will get a copy of that and take it. Think about those big pictures. Okay, think about the big pictures. I did a lot more with stats than anything because I, again, find that's the hardest material. And believe it or not, most of the questions I saw in the major field dealt with those concepts. But it's hard to separate stats and methodology. They really are one and the same. It's just the way we present them makes them seem like two different courses. Yeah, we're going to talk about issues of both in each course. So, Dr. Robertson, you wanted to give me time to answer some questions.
Yeah. So another component of this capstone course is to look at psychology as a professional. So whether or not that is you're directly applying psychology as an LSSP or as a counselor or something else in a clinical setting, or if you're doing it in a research setting. So what I'm going to do is every time we have a guest presenter, I'm going to ask them to just give us a little bit of their career history and a little bit of how their research might be being applied elsewhere. So there might be some non-psychological applications to psychological research. So if you don't mind, just how did you come to be a professor, and then what are some of the applications for your research?
Yeah, so quick and dirty, and most everybody out here has heard this just by having me in class before, but I always wanted to be a professor. The problem is I was going to be a math professor, and so I spent first, I guess I was in my mid to upper 20s when I switched fields from mathematics to specifically experimental psychology, and went that route. But I became a professor because I wanted to teach. I wanted to do exactly what I get to do every day. I didn't know the research end as much when I was a kid, like when I was going through high school and particularly college. I watched what my professors did in the classroom. It wasn't until about the end of my undergraduate career that I realized, the thing about being a professor that's different from being a public school teacher is not only do I get to teach, but I also get to, play with cool stuff, and do research and whatever that means. In mathematics, it was different from what we would consider as research in psychology, but the game is the same. The game is finding new knowledge, finding out how certain things work, finding out the mechanisms behind whatever phenomena that you're interested in. And so while it used to be something within pure mathematics, it became, for me, I really wanted to figure out what made certain people good at math and certain people not good at math.
And then, of course, that's a really huge question. And if you guys go to grad school to do some research, you're going to start out with a question about that magnitude. Your advisors are going to say, okay, tone it down a bit, Chief. All right? And that happened to me, and so I wound up in an area called math cognition. And that's essentially the cognitive processes that are involved when you think about numbers or do math, do basic arithmetic. And so while I was interested in things like calculus at the time, I'm now spending my career trying to figure out how people do basic arithmetic, which means by the time I retire, maybe we'll be thinking about how they do calculus. But right now, we still don't even know much about how they do basic addition. And turns out that no matter how studied you think something is, there's going to be so many open questions about it because just what we know about human behavior, even though there are textbooks and textbooks and textbooks, what we really truly know about the depths of human behavior is so minuscule. So for me, research is a daily part of my job, and doing stats is a daily part of my job, and it's just one of those things that excites me as a professional. It's why I do what I do, and I enjoy doing it. As far as application, we just talked about this in my research class yesterday. I'm a basic research scientist. That means that the questions that I do are not for the aim of direct application, but since I work in how people make mental representations of numbers and when the processes involved there's clear applications to education that could occur once we understand them a bit more. But as far as direct application, maybe there's something out there. I don't know. But again, the point is, I enjoy what I do from the basic standpoint, so I don't do what I do because of the applications. But many people, that's exactly what they do. They do research for the application. It's totally however you're wired.
Anybody have any questions as we are wrapping up, career-wise or about the content that we've covered?
Remember 50, 34, 14.
All right.
And there's no difference.